All right, I'm thinking it's just going to be you and me tonight.
Not the first time.
That's all right. I do think some people watch these afterwards, but you get to kind of ask whatever questions you want. Not that you couldn't anyways. So I'm going to start first. I'm going to share my screen here on my computer because I want to go through a few things that are on Blackboard anyway. And let's see. Do you see my Blackboard screen here?
Now I do.
Okay. So I just want people to know kind of where some resources are as they study. So first, under the resources tab here, this kind of has a lot of different things on there that we've used along the way here. And as we go towards the bottom, we can see that there's an Appendix C, and I think some people have kind of looked at and used this already. I encourage people to become comfortable with it because this is going to be something that we'll utilize in some way, shape, or form on the exam. There may be portions of this that are kind of projected. That's actually what's going to happen with the quiz tomorrow. Is I'm going to project some information from this, but just so that everybody knows that there are Ka values for anything that's a weak acid, noting that if there are 2 or 3 values here, these represent things that are polyprotic acids, so have more than one proton to remove. And we sort of talked about these very, very generally. We're not going to do a lot of calculations that are complicated with those, but those are our Ka values. And there's a lot more weak acids than we have weak bases, but here's our weak bases. One of the things I want you to note that all of these are actually amines. They are these amine bases. So when we see these atoms together, nitrogen bonded to hydrogen, that's going to be what we call an amine. And so we have Kb values for these guys. And so that's what's listed there. We've got a couple of pages of Kb values. We also have some Ka values for metal ions. We didn't get a chance to do a problem in class with this, but if you have a salt that has one of these metals, and let me zoom this in here so it's not super small. If you have one of these metals, we're going to learn about this in tomorrow's class, but when you have water that's bound to that metal, that water actually becomes much more acidic, and that water becomes a fairly weak acid so that it can generate an acidic solution. So from a qualitative standpoint, if you have a salt that has one of these metals in it, it's actually going to generate a solution that has a pH less than 7. It's going to be acidic. So I want everybody to be familiar with Appendix C, or knowing how you'd look at a subsection of Appendix C and be able to use that information to do problems. So that's Appendix C there. Any questions on that, Sarah?
Nope.
Okay. And then under our learning units here, I want to show you where a few resources are that will help in kind of studying, because this skill that we're going to have our quiz on really layers on a number of different things. One of the first things you need to be able to know is, and I will give you a chemical formula for tomorrow's quiz. It won't be a name. But you do need to be able to know, and here's some flashcards that can help. You need to be able to know if you see hydrochloric acid as a word, you need to know what the chemical formula is, as well as whether it's a strong or a weak acid or a base. Okay, so there's a list of 34 flashcards that are here that can kind of help you if you want to just have those to practice. So I wanted to make sure everybody knew where that resource was. Couple of other resources that could be helpful. If you go all the way down to the bottom here, in blue here are some extra kind of practice problems, and I've grouped them in 3 categories. So these first ones are extra qualitative acid-base problems. So if I just kind of start this quiz, these quizzes are all multiple choice, or it's something where you have to provide a single value for. And you will know the answers as soon as you sort of submit them. So if you don't get them right, you can see, oh, well, was it just Blackboard being stupid and not knowing that I had the right answer, but I just had too many significant figures or something? Or if it's a multiple choice question, it'll let you know what the right answer is. But this first one is qualitative acid-base problems. So some more just practicing hey, if you have KNO3, is that going to be a solution that is a strong acid, strong base, weak acid, weak base, or neither? Okay, so a bunch of questions kind of dealing with some qualitative aspects of acid-base chemistry. Here's a few questions on kind of writing conjugate either acids or bases for molecules. And then again, indicating when you have a certain solution, is it going to be having a pH greater than, less than, or equal to 7? So very qualitative here. So 12 questions. And once you take this quiz, you can retake it. I've got banks of questions that I created. So go ahead and retake the quiz. You're going to get another set of questions that are different. So I encourage people to sort of try these quizzes. So this one was qualitative acid-base stuff. Then if you need some help kind of doing these round the block calculations. So this is a quiz. And again, every time you do this, you'll get a new set of questions. So you can kind of retake them. So here is, what's the hydroxide concentration if you have a pH equal to 9.1? What's the KB for a generic acid if the pKa value is 3? So just kind of doing some of those round the block sort of calculations. So some simpler calculations, not ICE table based. And then the last one here is one that if you were to click on this, I think there's 4 problems as part of this. You'll always have a new problem if you kind of choose to take it again. But these are the kinds of problems that you're going to see on the quiz tomorrow. What's the pH of a 0.735 molar isopropylamine solution? So it tells you to use Appendix C to find the relevant equilibrium constant values. So there's 4 problems that you can try doing something with, and then kind of seeing what value you get. I will tell you, for these multiple choice questions, each one of the incorrect answers is a wrong turn that's common for students to make. So all of these numerical values are ones that you could get, but by taking the wrong turn. So it could be a good way to kind of practice some extra problems. So beyond that, what I wanted to work on today was, and just highlighting too, this is our salt equilibrium problems. So here, again, if you haven't yet seen how these work, if you click on kind of the PDF link here, you'll see the problem, which already has the worked out solution, but I encourage you, kind of block it off so you don't see that. You can see sort of the question here. So this is a qualitative one, kind of asking us to think about whether the solution is acidic, basic, or neutral. So you can kind of click on that and you can get the question. But then if you click on this link up top, you'll actually get to a YouTube video that will allow you to hear me walk through the answer. So if you look at the static solution and you don't quite get and understand the problem, you can actually watch the video solution to hear an explanation, or if it's a computational problem, see me sort of go through it. I would absolutely encourage you with these problems. You're going to want to probably kind of make it full screen. This was the old school way of me making videos, where I actually was having my iPhone kind of on a tripod to kind of record a paper. So it's a little bit more low tech than my iPad videos. So those are some resources that are available for you. I'm going to pause for a second, Sarah, see if you have any questions. And then I had 3 problems that I was going to work through tonight. I think once we do 3 problems, it just kind of continues. It gets to be a bit repetitive. So I think we'll have a shorter session tonight, unless there was other things, Sarah, that you specifically wanted to work on. But I had 3 problems I was going to run through.
Nope, that all sounds good.
All right, let me get my iPad connected here. Oh, let me stop sharing this screen. And I think the challenge with these problems right now, and you might see it if you do the multiple choice kind of like practice questions, it's very easy to get what appears to be a right answer, but it's not right because of a wrong turn that you took. So once I get my iPad here connected, I'm going to talk to you about some of those common wrong turns. And again, I know we talked about this in class on Monday, but it's certainly worth mentioning again. All right, share content. All right, so let me come back here. This was kind of an important slide. I sort of told people to take a picture of it when we were in class because these are some things I always want to make sure that you're asking yourself kind of this checklist of questions as you're going through the determine the pH of a solution. Again, first making sure that you look at what's in solution, particularly if it is a salt problem, that you dissolve that salt in water and eliminate things that are spectators. I'm going to comment here. I had a conversation with Abigail after class, and she brought up something that was, I think, an important thing to mention, that ammonium ions, that's the only sort of cation that we've seen that is part of a salt. So when we have NH4 plus, every other time we see a salt, it's going to be a sodium or a potassium cation, but you can have an ammonium ion. Now, what was a little bit confusing to her is we always crossed off sodium or potassium because we're like, oh, those spectators, you remember them from when we did precipitation stuff? Those were spectators. And even though ammonium would be crossed off as a spectator in our precipitation chemistry, we don't cross it off with our acid-base chemistry. So that was something, I was glad she sort of brought it up because she was a little confused by it. And I'm like, oh, that totally makes sense. Like we eliminated all three of those categories, sodium, potassium, and ammonium as spectators when we did precipitation stuff. But only sodium and potassium are going to be spectators with acid-base stuff. Ammonium is actually an important contributor to pH. So big picture here is, yes, don't consider things that are spectators, but you have to ask yourself the question, who is in solution? And that's going to be an important thing as we move into our next learning unit, which is going to be thinking about kind of doing things when we have multiple species in solution. So then we have to make sure that we write the equilibrium equation for the correct chemistry. Again, identifying whether that species that we have in solution is acting as an acid or a base. And then when we write our equilibrium expression, we have to make sure that we use the corresponding Ka or Kb value, understanding that particularly with salt problems, sometimes we're going to have to do that Kw equals Ka times Kb equation to get the corresponding flavor of the equilibrium constant that we need. So that's a common mistake, is that, well, first common mistake is people don't correctly identify whether they have an acid or a base equilibrium equation. And then they don't necessarily use the corresponding correct equilibrium constant value because they often have to do that Kw conversion. And then they forget maybe if their X is giving them hydroxide concentration, then it's a couple of calculations to get to pH because you have to go around the block. Okay, so just an opportunity to review a few things because usually like the skill that I test you guys on usually is something that kind of is the culminating skill in a specific learning unit. So all of those other things are important, but this skill that we did in Monday's class really kind of brings everything together from those previous skills. Okay, so we spent time in class and we did one problem. It was really great. I think most people got to work through and get this number. So that was really great. So the plan right now is just to give you 3 more problems to work on. And Sarah, since it's just you with me, I'll wait for you to sort of tell me whether you're done and you've got the right answer or you're ready, because you've kind of worked as long as you can and you haven't gotten the right answer. And some of these I'm going to give a little bit of a just a clue because it's not maybe the typical salt that we might have seen. It's kind of a drug or something like that. So just to kind of explain it a little bit. But here's the first problem we have. So this tells us that codeine, again, just there's always a little story to tell with a chemical molecule. So codeine, and there's a big chemical formula for it, is a narcotic pain reliever that forms a salt with HCl. Okay, what is the pH of a 0.05 molar codeine hydrochloride solution? Okay, so this is where I think this one's a little bit confusing. I want to make sure to set up the salt dissolving situation for you, because it tells us that we've got codeine as a salt with hydrochloric acid. Now this seems a little bit weird, but what it really means is that that salt really has the coating with the H as the cation, and then the Cl as Cl minus as the anion. So we essentially have something here that sort of resembles what we thought about doing when we had NH4 plus. So kind of keep that in mind as you think about NH4 plus. This was a molecule that acted as a weak acid. So that's the same here. We've got that guy who's going to be acting as a weak acid, but we're given the pKb value. Okay, so Sarah, I'm going to let you play with this for a little bit. I'm going to be right here. I'm going to let you work for a little bit, but I don't want you to struggle for too long. If you get to a spot where you're like, I don't know what to do here. These problems are a little bit more involved than what you're going to see tomorrow, and I'll tell you the ways that they are when we go through it. But I want to see if you can kind of work through this. I'm going to let you work for a little bit. Just let me know if when and if you get to a point that you need a little direction, and we'll do that for you.
Okay.
I'm going to be here, but I'm going to mute my video and my mic. And do me a favor, Sarah, just so I don't miss something in the chat, just unmute yourself and say, I'm done or I'm ready whenever you are ready.
Okay. I have a question. Are you there?
Yes, sorry. I'm doing other things on my computer, so I have to like navigate back to where I'm at. So what's up?
I don't know how to convert a PKB to a KB. I know that a PKB is the negative log of the KB, but I don't know how to reverse it.
And I will say, this is one thing that on your quiz, you're not going to need to know how to do, but it is an important thing to think about. So let's remember this, and I'm going to do this very generically. If you have, let's see, some quantity A, okay, if you take the negative log of that A quantity, that will give you P A, right? So the negative log of a quantity gives you PA. To go in the opposite direction, if we have PA and we want to go back to A, we take 10 to the minus A. So P 10 to the minus, I don't have values with this. So my analogy sort of fell apart here. Let me do it with pH because I think it's easy to think about that. Sorry if that was confusing here. So let's just actually do it with pH. So H plus concentration, right? We can get to pH by taking negative log of the H plus concentration. Okay. But if we want to go in the opposite direction and I want to take pH and go to H plus concentration, it's 10 to the minus pH. So for this case, if you've got a PKB value and you want to go to a KB value, it's going to be 10 to the minus PKB value.
Okay, and that's going to give me the KB value.
That will give you the KB value. Now, I'm going to ask you, is the KB value what you want to have for this problem?
No, it's not. I need the Ka value because this generates an acidic solution.
Perfect. Excellent. Okay, keep working.
Okay, I got it.
Yay! Awesome. Okay, so for people who are watching the video and need to see or hear an explanation for it, I am going to go through it a little bit more slowly to kind of walk through the solution. So again, there's a lot that's on the slide, so I'm just going to take it one step at a time. Okay. So first piece is, again, recognizing that this codeine HCl is a salt that dissolves in water to generate, oh, no, this is wrong. This is a weak acid. So let me fix that. Oh, come on, too big of an eraser. There we go. So it generates this protonated codeine molecule, which is a weak acid, plus water, and then chloride we know is going to be a spectator ion here. Just noticing as I'm walking through, like looking through here, we need to have this codeine has its H plus here. So codeine with its proton, when it encounters water, is going to break apart into codeine, which is the conjugate base, plus H plus. So things that are important to do is recognize that, hey, this salt generates a weak acid in water. So I have to write an equilibrium equation that shows that acid behavior. So again, if you didn't have this exact equation right, as long as you had the nuts and bolts that were right mathematically, you'll still get the right answer. So it's important that we realize that we generate H plus on the right side here. Okay, so when we write an equilibrium expression, we're recognizing that it is a Ka value. Now, again, this is what we talked about, Sarah, when you had a couple of questions as you were starting to work through here. Okay, we have a pKb value that is given. And so we need to do 10 to the minus pKb in order to get the Kb value, and highly important, right, that we recognize that Kb value is not going to be the numerical K that we need to use. We need to use a Ka value. So you need to do a little bit of conversion there, and I don't have it written down here. You need to do a Ka value. You need to get your Ka value by using Kw. Okay, so that's going to allow us to get to our Ka value. Okay, so rest of the problem looks the same as stuff that we've done in our last learning unit on equilibrium. And then even when we did problems in class on Friday, when we were dealing with just doing weak acid and weak base equilibria. So we've got our ice table here. Remember, the concentration that we have of this guy is going to be equal to these as well, because it completely dissociates. So that number becomes this piece in our ice table. We know we're going to have a little bit that dissociates and makes a little bit of the conjugate base in H plus. So here's our equilibrium row in our ice table. So again, our Ka value that we have here, and you know what, I apologize. As I'm looking through here when I did this is Kw. So that I did have this equation here. So Ka equals Kw divided by Kb. So that's how I get that 6.31 times 10 to the minus 9th. Okay, so I'm going to kind of put over here, this is an equation that you won't be expected to know. It'll be provided for you. Kw equals Ka times Kb. Now, the more of these that you do, you'll just kind of know that that's the equation that you need to use, but it will be provided for you. And then Kw mathematically is 10 to the minus 14th. Okay, so going through and doing our solving for X, we're going to be able to use a simplifying assumption. And that's going to allow us to solve for X. Sorry, the boys just got home from soccer practice and Charlotte is making some noise. So we're going to have our H plus concentration is equal to our X. And so this is going to be, yes, loud noise. I'm recording a class right now. Sorry. And so we're going to have our H plus concentration equal to this number. I told people in class too, please do not round too early, because even though I give you sort of plus or minus 5% when you put in your answers to Blackboard, if you round too much too early, that might be more than 5% different, and it'll unfortunately get marked wrong in Blackboard. So since our X is equal to H plus concentration and we want pH, negative log of that number is going to get us to our pH, which is 4.75. You're not required to do a check, but it's always a good idea to at least mentally sort of do it. And if you want to do that 400 rule beforehand, that's fine. But checks are always whatever your X value was divided by the size of the pile that you started with. So that's going to be your concentration initially times 100. Make sure that that's not greater than 5%. So any questions on that, Sarah, before I give you another one to try?
Nope.
Okay. So I think once you see the pattern, and Sarah, you're really good at kind of recognizing patterns in things that we do. It's just making sure that you're meticulous about the things that you do to kind of go through. Highlighting again, common places that students make mistakes is they would use a KB value in here, and that will give you the wrong answer. If you have a problem where your X is equal to OH minus concentration, they'll just take the negative log of that, and then they think that's pH. But we should have, our logic hat on and say, oh, if I had a qualitative problem that said, what would the pH of the solution be? We would say acidic. And so we've got kind of a logic hat that if we got a number that was greater than 7, we probably knew we made a mistake. Okay, so here's another problem to work through. Okay, what is the pH of 0.1 molar sodium phenolate? So here's the structure for sodium phenolate. This is the sodium salt of phenol. Okay, so you're going to want to use Appendix C to kind of get some values for you for this problem. So the answer should be 11.5, but go ahead and work through this problem.
All righty. Okay, I got it.
Awesome. Okay. So again, I'm just going to walk through this in case anybody needs a walkthrough from it. So first step we always want to have is we want to find out who's in solution. So because we see that there's a sodium cation there, we know we have a salt. So all sodium salts are soluble. So this sodium salt is going to dissolve in water and generate this phenolate anion and a sodium cation. Sodium cations are spectators when it comes to acid-base chemistry. So then we need to think about whether or not this guy is going to have any acid-base potential. So remember, the mental thing that we want to do with this is we convert this into its base, or I'm sorry, into its conjugate acid. So just kind of mentally, we're going to convert this into its conjugate acid. And so it's going to be this guy, which is phenol. Okay, so this problem also tells us that what we made is the sodium salt of phenol. Okay, so we look up phenol on Appendix C, and we can see that it is a weak acid. Okay, so, but we don't have phenol in solution. Okay, we've got the conjugate base of phenol. So that conjugate base of phenol in the presence of water is going to take a proton off of water. It's going to leave behind hydroxide, which is why my solution is going to be basic. Okay, and it generates that conjugate acid. So this is the species that we have an equilibrium constant for. Okay, so we know that we've written a KB equation. We've written a base equation. So we need to have a KB value. So again, KW minus or divided by that KA value is going to be how we get that KB value. Okay, ice table is the same as we've always seen. Okay, this concentration of the salt becomes the concentration of the conjugate base, which is what our equilibrium is based on. So that's our initial concentration there. Nice thing, remember, with acid-base equilibrium equations is the stoichiometry is generally 1 to 1 to 1. So we don't see anything in front of our x's here, which also means we don't have any squared terms that we need to be concerned about, or cube terms. We saw a lot of those in our last learning unit. Make a simplifying assumption here to make our algebra easier. So you're basically then going to be solving for x. The challenge here with this problem is our x is going to be giving us a hydroxide concentration. So that's one of those things we have to make sure that we don't just take the negative log and be like, whoops, we're done, right? We should have our logic hat on that says, wait a minute, basic solution. I should have a number for my answer that is greater than 7 for my pH. And that should be a reminder, oh, that's right, I calculated POH because I took the negative log of the hydroxide concentration. So 14 minus that number, that around the block calculation is going to give me my pH of 11.5. Okay, I'll always show you a check just because it's a good thing to do. In this case, our check still falls within the 5% rule, so that was okay to make a simplifying assumption. I am not going to give you a problem that will fail your check, but it's just a good practice to kind of be in. Questions, Sarah?
Nope.
Okay, I've got one more problem, and then the fact that you've gotten the first two out of the gate here, right, has me having great confidence that you're sort of good with this. If you wanted to do any more practicing, you could sort of, again, practice those multiple choice questions to see if you get the right pH for those. But here is one more to try. What is the pH of a 0.88 molar pyridinium chloride solution? Okay. So again, there's the structure for pyridinium chloride. The pH for this solution should be 2.64. Okay, so go ahead and try to work through that calculation.
All righty. Okay, I got it, but I have a question.
All right, go ahead.
So
What's your question? Yes.
I solved this as a KB value,
Mhm.
getting a POH of 2.64. And then I saw that that's what you got for the pH.
So let's look at the solution here and see. You may have gotten lucky because sometimes if people make two wrong mistakes, they can still sort of get the right thing. So let's look at what we have here. So again, here, this is like the codeine problem, where this is kind of like this was codeine as an HCl salt. So when this dissolves in water, we get chloride as a spectator, and then this guy, which is a weak acid.
See, that's where I messed up because I thought it was a weak base.
Mm.
And then
So I guess well, so you may have been taking, if you took two left turns, you may have, inadvertently gotten to the right, maybe.
maybe. Yeah, no, so, looking at Appendix C, what I saw in there,
You saw this guy, you saw a
Yeah.
KB value.
maybe I did. Let me look again. I'm looking at it on my phone and it's really small. So I may have looked at it and thought it was a Ka value.
Hmm.
Okay, yeah, it's actually Ka. Sorry, I actually should have been wearing my glasses. I thought it said Ka value when I saw that on there, so then I thought that, okay. That's where I messed up.
Okay. So let me just kind of walk through the rest of the solution for anybody who needs a walkthrough. And then if you have some additional questions, we can sort of go through that afterwards. So again, and this is, it is a challenge to say, all right, this is the guy that I have. What does it make in solution? And then once I figure out who's in solution, who has the chance to do some chemistry? Chloride's always going to be a spectator from an acid-base standpoint. Okay. And then the counterpart to this, and again, even just looking at the molecule that we have here, once we have this, we can see that what we have here is something that has a positive charge on it. So that must mean the option for this is to be a weak acid, okay? It is the conjugate acid of a weak base, and this is the weak base that we're gonna find on Appendix C. So we predict that the solution is gonna be acidic, so I'm going to write an acid equilibrium equation. So that's this guy losing its proton to water to generate H3O plus and leave behind the conjugate base. Okay, and that's the value that we look up on Appendix C. So now the numbers just kind of come in here. That's going to be our initial concentration of that weak acid. Go through, and again, because this is a KB value that's provided, but my equation and my corresponding equilibrium expression is an acid equation and expression. I have to use a Ka value, which means I need to take Kw and divide by my Kb value to get this guy. And then I can solve my ICE table for X using a simplifying assumption. So X is going to be 2.275 times 10 to the minus third. That again is going to be my H3O plus concentration. Because this problem directly gives me X as H3O plus, just a simple negative log of that will give me the answer. pH is 2.64.
Yeah, I was using all the right numbers. I just had it mislabeled because I
Okay.
misread it. I couldn't see it. It was too small on my phone.
And hopefully that's not the case tomorrow. So just to let you and then anybody else who's watching this know, what's going to be projected up on screen is going to be a subset of values from Appendix C. Okay, because I have a whole bunch of different problems that grab different kinds of molecules. So depending on what your molecule is, you'll grab that species off of the subset table that I kind of have available. So hopefully it's something, hang on a second, JT. Oh, JT, can you just peek in the oven and see if this stuff's done? Okay, I'm almost done here, but then I'll be able to get your pizza out. All right, so that kind of wraps up. I figured if we did 3 problems tonight, that probably was going to be sufficient, especially if people were kind of getting getting these down. And it sounds like you were 3 for 3 here. So I think you're probably pretty good. Just make sure to go through those checklists. It is a little bit easier here with this, right? Because you knew the answer you were trying to get. So when you got to that answer, you're like, yay, I got the problem right. So just make sure to use those same logic checks tomorrow on the quiz.
Yeah, and wear my glasses.
And wear your glasses. And this is always the case. Don't hesitate. You know, I know things get small in the back of the room. You can ask me to zoom in on something, on anything that's projected on the screen, but everything else should be available for you via Blackboard on your computer.
Okay, can I ask you a question about ChemLab when you're done recording?
Yeah. So I'm
Okay.
going to stop recording and then you can ask that. All right.